Hello friends, this video on equilibrium part 3 is brought to you by examfear.com. No more fear from exam. Before watching the video, please make sure that you have watched part 1 and part 2. So let's take one example. A liquid is in equilibrium with its vapor in a sealed container at fixed temperature. The volume is suddenly increased. What is the initial effect on the change of vapor pressure? Well, how does the rate of evaporation and condensation change initially? And what will happen if the equilibrium is stored finally? So let's take the same container. We have this dish of water here and it is in equilibrium. Now the volume is increased. This is increased now. Let's suppose this has become this big size. The volume is increased. So obviously the first question says effect of change in pressure. So pressure will decrease, right? Why? Because we have told that volume and pressure are inversely proportional. So increasing the volume of this, the pressure will definitely decrease. That is my first. Let's take second. How does the rate of evaporation and condensation change initially? See, the rate of evaporation is dependent on what? So rate of evaporation is dependent on temperature only, and the chemical and temperature and the chemical compound. So if my temperature is not changed, chemical compound is not changed, the rate of evaporation will not change. Will not change. Let's talk about the rate of condensation. If you talk about the rate of condensation, it is dependent on what? The vapor pressure. Or vapor pressure. So if vapor pressure is decreased, the rate of condensation will also decrease. You understand this? See, rate of evaporation, whatever it will evaporate here, that depends on the temperature and the chemical compound of the material we're talking about. For example, water here. So water is not changed here. Now the temperature is changed. It's the room temperature. The fixed temperature actually it stays here. So rate of evaporation will not change. But condensation, if you see, you must have seen, it depends on the vapor pressure, right? So initially there is no condensation. Now it will evaporate more. The vapor pressure will go up and then condensation will start. So since the vapor pressure has decreased, the rate of condensation will also decrease. Done. Third, what happens when the equilibrium is finally restored and what will be the final vapor pressure? See, when the equilibrium is finally restored, the vapor pressure will be same. Because I told vapor pressure at the equilibrium is not independent, is independent of the volume. If you take big volume, small, it doesn't matter. It's independent of the volume or the amount of water you take. It's the property of the substance. So vapor pressure will be restored. And if you talk about the vapor pressure, the rate of evaporation and the rate of condensation at that time, so that time you will see the rate of evaporation will be equal to rate of condensation. So what will happen here? The moment you increase the volume, the vapor pressure will decrease, so the condensation rate will also decrease. So more and more vapor will be evaporated. Once more and more vapors are there in the system, the vapor pressure builds up, right? And then when the vapor rate of evaporation and when the vapor pressure becomes the original vapor pressure, that time you see the rate of evaporation becomes the rate of condensation, and that time you see the vapor pressure is stored. See, if you take some water and some sugar here and try to dissolve, you see that you are able to dissolve. But if you add more and more sugar, you get this kind of solution. But you will see that after some time, you will see that some sugar crystals are still there and you are not able to dissolve it. Correct? Why? Because it has reached equilibrium. But now, if you heat this, if you increase the temperature, you will see that the sugar crystal which was not dissolved, it will get dissolved. That means this guy, dissolution of solids and liquid, is dependent on temperature. Also, if you see, if you got sugar syrup and if you cool down, if you cool this, what you will see this. If you cool it, you will see that the liquid, the crystals comes out. And that's what we do in crystallization, right? We cool things and we see that, we cool the solution and we see the crystals comes out. So that's why we see that when you talk about the dissolution of solids and liquid, it is temperature dependent. So let's talk about dissolution of gases and liquid. So dissolution of gas and liquid is not temperature dependent. I'll tell you first now only. It is not temperature dependent. It is governed by Henry's law, which says that the mass of gas dissolved in a given mass of solvent at any temperature is proportional to the pressure of the gas above the solvent. And that is how, if you see, when this Coca-Cola bottle is filled, it is filled at very high pressure, and that's why all these gases, bubbles get dissolved. But the moment you open it, the high pressure is gone. What you have is atmospheric pressure, which is much less than the high pressure, at which this bottle was sealed. The bubbles comes out. The bubbles comes out. Hope you are getting the point. So that is why even if you heat these or cool this, the bubbles won't come out, right? If you take a Coca-Cola bottle and you cool it or you heat it, you won't see bubbles. The moment you open it, the moment you put a change in pressure, you see the bubbles coming out. That means dissolution of the gas in liquid is pressure dependent. Let me write this. It is pressure dependent. It is not temperature dependent. So let's do a recap of what we have learned till now. So for a solid liquid equilibrium, it exists only at one temperature, that is the melting point. For a liquid vapor equilibrium, it also exists at a constant temperature. For a solid liquid equilibrium, we have like sodium, chlorine, water. It also exists at a common temperature. But for the gas liquid equilibrium, it is dependent on pressure, right? It is dependent on pressure. The other three things are, these three things are temperature dependent. So hope you will keep this in mind. You think that for everything it's temperature, only when you talk about Coca-Cola, it is pressure. The moment you open the bottle, when you open it, you get the bubbles. So that is nothing but the gas liquid equilibrium, and that is pressure dependent. So having studied various kind of physical equilibrium, let's understand the general characteristics of physical equilibrium we should overlook. The first and the most critical thing is it is possible only in closed system at a given temperature. So when my system is closed, my chemicals can't go out, heat can't go out. That time only you have this physical equilibrium. In open system, I can't get a physical equilibrium. It has to be closed system at a given temperature. The second characteristic is, in the physical equilibrium, both the forward reaction and the backward reaction both take place simultaneously, and it is dynamic. It is dynamic, both forward reaction, backward reaction, and they take place simultaneously and they are equal, right? So that's why we see both the opposing processes occur at the same rate at the same time. So it is dynamic also. And when you have equilibrium reached, all the measurable properties are constant. You have seen also in the cases where the pressure is constant, the volume is constant, temperature is constant, all the measurable properties we have is constant in the equilibrium. So when the equilibrium is attained by physical process, it is characterized by constant value of one of its parameters at a given temperature. That's why it says that all the measurable properties are constant. The magnitude of such quantities at any stage indicates the extent to which the reaction has proceeded before reaching the equilibrium. So, for example, I have the lot of ice and it was at temperature, now let's suppose 5 degrees Celsius. You see out of 5 ice, very few of them, let's suppose 10% of them melted. But again I have some ice and this time I have at 50 degrees Celsius. You see almost 90% will melt. Right? Because see, in both cases equilibrium will be reached. Let's not take 50, it's too high. Let's take 20 degrees Celsius. Let's suppose 80% is melted. So in both cases equilibrium is reached, but in one case 10% of the ice got melted, another person 80% of the ice got melted. So both determine the extent to which the reaction has taken place. Here when I'm talking about reaction, I'm talking about the conversion of water from solid stage to the liquid stage. Correct? So we will talk more about this when we talk about how to find the extent to which the reaction has taken place. Right? But the magnitude of such quantities, as I told, right, it will have constant values. So it will have a constant value for the water or constant value for the ice. All those things will determine the magnitude or the extent to which the reaction has taken place. So the first and the foremost requirement is it has to be in the closed system, fixed temperature, it is dynamic, all the measurable property is constant, and if you want to find how much reaction has proceeded before reaching equilibrium, you have to understand the quantities of the system actually, and then you have to calculate and find how much reaction the whole system has proceeded. Thank you. Visit examfear.com to watch free educational videos, try free online tests, get the best quality study materials, study from the best tutors and mentors, and much more. Thanks once again.